on the channel. In today's video, we're going to be solving this following differential equation. Oh, I just lost it. Here it is. So we're going to be solving cos x times by dy dx plus sin x times y is equal to 1. Okay. Now, when I first saw this equation, I thought it could be solved actually straight away without doing an integrating factor or any special techniques, just pretty much by using a perfect derivative, but we can't do it here because it is not a perfect derivative, because the differential of cos isn't sine, it'd be negative sine, and vice versa. Okay, so here what we have to do is, before we even solve this guy here, we want to try and get into a form like this. We want to get the first derivative pretty much to have a coefficient of 1. We want a function here, function of x times by y, and we want it pretty much equal to whatever's on this side here, but predominantly a function of x still. Okay, now because there's no really other y's in here, we can have that. So to pretty much get this differential equation into a form like this here in the green, all we have to do is divide by the cos x in front of that dy dx. Okay, so if I divide everything by cos x here, and cos x here, this is what we're going to get. Okay, so now I'll just make this black so it stands out a bit more. We're going to get this following expression. So we'll get dy dx plus sine over cos, which is just tan x y, equals 1 over cos, which is just sec pretty much. Okay, because 1 over cos x is sec. Okay, with respect to x. Alright, now we've got it into a form where this is actually quite good. So we actually have it in a form like this. So dy dx plus a function of x, so p of x times y, and another function x here. Now, what we want to do is we want to try and make a perfect derivative on this side here. Meaning, we're going to introduce an integrating factor. Now, when we're introducing an integrating factor with a structure like this generally, we're going to multiply both sides of the equation by e to the integral of whatever this function is in front of the y here. So whatever this guy here, we're going to integrate it and put it to the power of e. Okay. So in this case here, if I were to move that to the side, up there. Oh, that's funny. Let's go here. So in this case here, we're going to use the integrating factor e to the integral of tan x dx. We're not going to account for the constant up here because it's not really going to be relevant at the end. Okay. We will add a constant at the end though, just to account for pretty much solving the differential equation, but it's not really important up here. Now, what is important is to integrate this guy here. Now, at the moment, this probably isn't that great to integrate, so what we're going to have to do is pretty much just rewrite it like this, as sine over cos dx, and what we're going to have to do is pretty much just integrate this integral here. Now, what we have to do here is we have to do u substitution, meaning we usually pick the biggest algebraic expression to make u, but in this case here, we're going to choose the denominator. Because it's a function divided by function, and there's no significant powers here, and they're just both the same order, and they're both cyclic, we're going to have a log structure appearing. So what I'm going to do is let u equal cos x, and I'm going to change everything to this new variable u. So meaning I want to replace the dx with a du, so du dx differential, this is going to be negative sine. Meaning, if I were to get dx as the subject, dx is du over negative sine x. Meaning we can replace this into there, and we can replace this into there. Meaning this transforms into, so sine x over u du negative sine x. And we can see those cancel out. So what we're left with is negative, I'll take the negative at the front, 1 over u du. So negative ln u plus c. If you want, you can have the absolute values here because they can only take a positive input there. And then we just put the u back in here. Now, I just wrote plus c because that's what I do naturally, but in this case here, we're not going to include the plus c in our expression because this is going to be a part of the integrating factor. Okay, so all we need is this guy here. So I'll just copy that and bring it up. Actually, I might bring all this down, that way it's a bit easier in the long run. I'll just bring this whole thing down, go here, and then I'll bring this guy down. So here, because we know that is what that turns into. We can rewrite it like this. So e to the negative ln cos x, absolute value. Now what we can do here is we can pretty much pull the negative on the inside but raise it to the power. So we can rewrite it as e ln 1 over cos, because these guys are inverse functions, these are going to effectively cancel each other out, just leaving whatever's here in the power as the only thing remaining. So what we have is just 1 over cos x, which is just sec. So our integrating factor we're going to multiply everything by is just sec x. Okay. So here what we do is we take our differential equation and we're going to multiply both the left hand side and the right hand side by this term. So times this on the left hand side and the right hand side, which will give us this: sec x dy dx plus sec x tan x y equals sec squared x. Okay, now let's try and break down what we have here. So first of all, let's try and simplify this, because we do have a perfect derivative on this side here, but it's actually not that obvious straight away. So here, what I'm going to do is I'm just going to copy this differential equation, just write directly underneath, but I'm just going to change these terms here. So here sec is the same as 1 over cos x, and tan is the same as sine over cos x. Okay, so if we want, we can think of it like this here, and if we want, we could write this one as well as just 1 over cos. Now let's understand what we have here. If I were to differentiate this, what would pretty much happen? Okay, so if I were to differentiate 1 over cos, I would have to treat it like this: the differential cos x to the negative 1. Okay, now when I differentiate that, that has to come down to the front, so I have negative cos x all to the power of negative 2. Okay, then I have to multiply by the differential of the inside function, which is cos x, following chain rule. Now the differential of cos x is negative sine x, so I have to times it by negative sine x. And here we get pretty much a negative times a negative, so that's a positive. So what we have is pretty much just sine x, and if I make that a positive index, over cos squared x, which is exactly what I have here. Because if I were to multiply these guys here, I would have sine x over cos squared. Okay, so effectively what we have here is a function which we'll call u, the differential of that function, another function's derivative v dash, and the actual function here. This is the product rule. Okay, so what this means is we have a perfect derivative here because we have a differential pair and the function next to each other twice. So what I mean by this is, alright, this function's derivative is right there, and this function's derivative is right there. So this is product rule, meaning this could be represented as the derivative of sec x times y. So this entire left hand side here that I'm going to highlight is the same as this. Because if I were to expand this out, this would have to be product rule, meaning I have to diff that, leave that, plus diff that, leave that, etc. Okay. Now, reason why this is good for us is because I want to try and get y as a function. I want to get y by itself to solve the differential equation. To undo this operator, all I have to do is integrate both sides with respect to x. So the mechanics behind this would literally just be this. If I were to copy this again. Oop. This is what I would be doing. Integral dx, integral dx. This cancels out the operator overall. So what we're left on the left hand side is sec x times by y equals the integral of sec squared dx. Okay. Now, the integral of sec squared dx is tan x. Okay. So tan x here, and then we have to include a plus c to account for any number that could have been on that side. Alright, and we're almost there. So all we have to do is divide both sides by pretty much sec x. So y is going to be tan x over sec squared x, sec, plus c over sec x. And then pretty much all we have to do is just simplify this, so this can be rewritten. Because that's cos, we could write that pretty much as, so tan over sec is the same as sine x over cos times by cos plus cos x with a constant c. So this can be written as sine x plus a constant c cos x. Okay? And that's it. Now, for good measure, if you want, you can include another constant here to account for it, like a plus k or whatever, when we differentiate it. But this should be fine overall. Okay? But yeah, that's how you solve that differential equation. If you have any questions at all, leave something in the comments and I'll try my best to answer it. But I will see you in the next video.